Every animal on Earth stands to gain from language, yet out of millions of species, only humans ever broke the silence. Parrots can mimic sounds, apes can sign a few commands, but true grammar, storytelling, and endless invention belong to us alone. This evolutionary riddle sits at the heart of why only humans learn to talk, a question with stakes as deep as our survival itself. Because 135,000 years ago, our ancestors unlocked a code that lets strangers cooperate, warn of danger, and plan civilizations, leaving even the most talented animal communicators behind. If speech is so powerful, why haven't intelligent animals caught up? The answer rewrites what you think you know about being human. Parrots like Alex can say over 100 words, answer questions about color and shape, and even ask for his favorite treats. But if you try to have a conversation with him, ask about the past or why you want something, you run into a wall. No matter how clever the bird, the words never stack up into new, rule-based sentences. It's the same story with apes. Coco the gorilla learned to sign more than 1,000 words. Kanzi the bonobo mastered a board of lexigrams and could point to symbols for apple or give. Nim Chimpsky, the famous signing chimp, could string together signs like banana eat me or me nim eat. But watch the tapes closely. The signs come out as requests, never as stories. There's no spontaneous grammar, no new combinations, just a stream of imperatives. Give me, tickle me, more food. Researchers like Michael Tomasello have spent decades comparing human toddlers and great apes. The difference isn't just vocabulary, it's something called shared intentionality. The drive to build meaning together, to point, to teach, to check if you're following along. Even when apes learn hundreds of signs, they don't invent new ones or ask questions about things they can't see. Their communication stays glued to the here and now, tied to food, play, or immediate needs. Meanwhile, every 3-year-old human can tell you what happened yesterday, or make up a story about a dragon. Children break the rules, invent new ones, and expect you to keep up. That's the ceiling for animals. Mimicry, not invention. Syntax, not just signs. It's a gap so wide that even the best trained parrot or the most pampered ape can't cross it. So if parrots and apes are so close, what's holding them back? Maybe it's not just about brains or cleverness. Maybe something in the body itself is setting the limits. Tecumseh Fitch wanted to settle a long-standing question. Is the shape of the vocal tract what really blocks animals from talking? In 2016, he and his team placed macaque monkeys in an MRI scanner and mapped every twist and turn of their vocal anatomy, frame by frame. They found something surprising. The macaque vocal tract, with its flexible tongue, lips and throat, could, in theory, produce a wide range of vowel and consonant sounds, enough to mimic much of human speech. The limiting factor wasn't the hardware, it was the wiring. Humans have a descended larynx sitting low in the throat. That opens up the vocal tract, letting us make sharp contrast between sounds like e, ah, and oo. For decades, the descended larynx was treated as the secret ingredient for speech. But then, archaeologists unearthed a Neanderthal hyoid bone in Kabara Cave in 1989. CT scans and biomechanical models showed that this ancient cousin had a hyoid almost identical to our own, anchored for strong tongue and laryngeal muscles. If a Neanderthal walked into a modern clinic, their vocal tract wouldn't look out of place. Yet there's no evidence they left behind poetry or even simple stories. Other animals show bits and pieces of the puzzle. Chimpanzees have a high larynx and a more rigid tongue, limiting their vowel space. Parrots use a completely different system, the syrinx, not the larynx, but can still copy many human sounds. The real difference isn't just about bones and muscles, it's about how precisely those muscles can be controlled, how fast the tongue can move, and how the brain coordinates all the parts. Anatomy clears the first hurdle, but it doesn't get you across the finish line. Even with all the right pieces in place, something else has to flip the switch. The next clue lies deeper in the molecules and circuits that set humans apart. In the 1990s, a family in London found themselves at the centre of a scientific storm. 3 generations, grandmother, mother, children, struggled with speech so tangled that even simple sentences came out garbled. Doctors called it verbal dyspraxia, but the real breakthrough came when geneticists pinpointed a single mutation on chromosome 7. This was the KE family, and the gene in question was FOXP2. One tiny change in their DNA made it nearly impossible to coordinate the muscles of the face, tongue, and throat for speech. MRI scans showed that the affected family members had subtle differences in brain regions tied to language, especially in the left frontal lobe. The story of the KE family turned FOXP2 into the so-called language gene, though the reality is messier. FOXP2 acts more like a master switch, influencing networks that handle everything from vocal control to the timing of orofacial movements. But FOXP2 isn't the only player. Human brains come wired with a web of circuits linking Broca's area in the frontal lobe to Wernicke's area in the temporal lobe. These are the engine rooms for grammar and meaning. In MRI studies, Broca's area shows a leftward tilt, an asymmetry more pronounced in humans than in other primates. This lopsided wiring helps us juggle word order, tense, and nested clauses all on the fly. Even Neanderthals had a version of FOXP2, but the full suite of neural connections, especially the dense highways between auditory and motor regions, seems to be unique to Homo sapiens. The debate over how much of language is baked in from birth still splits the field. Noam Chomsky argues for an innate universal grammar, a mental blueprint shared by every human. Steven Pinker calls language an instinct, shaped by natural selection. Yet as Daniel Everett's work with the Pirahã people shows, culture and environment can sculpt the architecture of language in ways that challenge even the most elegant theories. Genes like FOXP2 and specialized brain wiring set the stage, but they don't write the script. The next leap from potential to performance needed a spark from outside the skull. That spark came from something uniquely human: the pressure to share, to teach, to build meaning together. At Dmanisi in Georgia, archaeologists found a skull nearly 2 million years old. Its owner had lost every tooth but one, and yet survived for years. No fire pits, no blenders, just a group that must have chewed food for him or shared the softest scraps. This isn't language, but it's something close, a form of compassion and cooperation that goes beyond what's seen in any other animal. The roots of language run through this kind of social glue, helping, teaching, sharing, not just surviving alone. Fast forward to the 1980s in Nicaragua. Deaf children, isolated at home, were brought together in a new school. With no shared language, they invented one. At first, their signs were rough and simple, but as younger kids joined, the language exploded. Verbs, subjects, even tenses appeared. Researchers filmed the change in real time, watching grammar come to life from scratch. It wasn't taught. It was built, child by child, in playgrounds and hallways. Culture didn't just pass language down, it let it bloom. But there's a catch. Language has a window. Jeannie, discovered in California in the 1970s, had spent her childhood locked away without words. Even after years of therapy, she never mastered grammar. Victor, found in the forests of France in the 1800s, faced the same wall. Both learned words, but not the rules that make sentences fly. The brain's door for language swings shut with age. A critical period that, once missed, can't be forced open again. And even among humans, the rules aren't as universal as once thought. Daniel Everett, after decades with the Pirahã people in the Amazon, claimed their language doesn't use recursion. No nested clauses, no the man who saw the dog that chased the cat. His claim set off a firestorm among linguists. If true, it means culture can shape language's deepest structures, not just its surface. Cooperation, invention, and timing, all three help explain why language took off in our species. But the puzzle isn't finished. If culture and childhood can unleash grammar anywhere, why did only humans cross the line? The answer still hides somewhere between our ancient need to connect and the limits of our biology. Human language emerged at least 135,000 years ago, marking a turning point no other species has crossed. As the documentary showed, even the most advanced animal communicators, Alex the parrot or Kanzi the bonobo, can mimic or signal but never invent grammar or true syntax. Anatomical changes like the descended larynx and changes in the hyoid bone, revealed by MRI and fossil evidence, gave humans new vocal abilities, but these alone were not enough. The discovery of the FOXP2 gene in the 1990s and unique brain structures such as the expanded Broca's area in Homo sapiens linked biology to this leap. Yet, the precise combination of genetic, anatomical, and cultural forces that unlocked speech remains partly unresolved. Today, every child inventing words or learning sign language echoes this ancient breakthrough. The evidence is clear: language is evolution's rarest invention, and so far, only humans hold the key.